So let's look at this term of half-life. You may have realized up till this point that whenever we're using K, it kind of was nonsensical. Like, what is a per year anyways? What does this unit really mean? Or, what is a per day? Is this a long period of time? Is that a short period of time? Like, what does that number mean? So we worked out half-life to give that number some kind of meaning. So we could just reference something's half-life and kind of immediately have a sense of what we're talking about. So for half-life, all you have to do for a first order, and these are both first order, is do that half-life is equal to 0.693 over K. And so it's just that 0.693 over the number that's shown right there, 1.209 times 10 to the minus fourth. And then for this one, T half, it's the same idea, 0.693 over K equals 0.693 over 1.824 times 10 to the minus 1. And that's a per day, and that's a per year. Again, really weird units. So if I take my calculator and I bring it up and actually do the math on this, let's see if this suddenly makes sense. 0.693 divided by 1.209 e to the negative fourth. So I'm going to go ahead and multiply that out, and it tells me that the T half is equal to 5756 years. Do you see how I did that times 10 to the third? So now all of a sudden we can talk about what we're talking about. This substance, when it's doing a reaction, it takes this many years for us to lose half of it. That makes a lot more sense in terms of our brains over this number, right? So let's see what the half-life of the other substance is. The radon. Radon kind of matters, right? We don't want radon in our homes. So that number divided by 1.824 e to the negative 1. So that gives me that my half-life, and I don't have any exponents on that one, is 3.8 days. So it takes 3.8 days for it to be gone by half. So hopefully that makes more sense about why we're talking about it. We also calculate it and use it for a few things, though. One thing is that we generally consider a reaction done after it's been 10 half-lives. And so if we started out with a molarity of like 10 after one half-life, we'll have 5. After another, 2.5, 1.25. You following what I'm doing here? I'm just dividing them by 2. Now I'm having a blank because I'm doing this on camera. 1.25 divided by 2. There we go. Yeah, 625. Then divided by 2 gives me 0.321. 3, 1, 2, 1, 2. Divide that by 2. And so then that gives me 0.156. Let me see if I've done enough yet. So this is 1 half-life, 2, 3, 4, 5, 6. I've only done 6 half-lives, but look, do you see how far along we've come in the half-life? We're down to this 0.156. So it also gives us a sense like how low is that going to go? And I'll just finish it on my calculator. I just need to divide by 2, a total of 4 more times it looks like for it to be, so 7, 8, 9, and 10. Yeah. So divided by 2, divided by 2, divided by 2, divided by 2. So that tells you that the amount of the substance is going to be 0.09765. And look at what a small amount that is comparatively, from 10 all the way down to that number at 10 half-lives. So generally we say that's when the reaction's done. It also can just be helpful to be like, okay, so 3.5 half-lives have passed, so we know that we're going to be in this-ish range right here. So you can talk about it like that. But all in all, that's why we have this half-life. Note that the half-life term changes. It still means the same thing. It's how much something is left after 50%. It's how long it takes for 50% of something to react. So this is only the formula for the first order. There are other formulas for the 0 order and the second order, but they all mean the same thing in terms of what half-life means.